So, welcome everyone. I'm going to be discussing page 10 from your handout. So you need to get your handout ready. Have that in front of you. Open it on the page with trigonometric identities and double angles. I'm going to first talk about these two trigonometric identities. They're like equations, but they involve trigonometric ratios. First of all, this one. Well, if we look at the unit circle and we have an angle theta here that leads to that point P being placed here, you will remember that the vertical component of that point, this part here, is sine theta, the horizontal component is cosine theta. Okay, and very simply, if I now look at this right angle triangle that I have, I can say, well, in a right angle triangle, tan theta is equal to the opposite over the adjacent. Opposite over adjacent. Now, so tan theta, where's the opposite? The opposite is here, and the adjacent is down here. But this is also cosine theta, of course. Okay, so basically, I'm having sine theta over cosine theta. So there's the relationship here between tan, sine, and cos expressed in that simple equation. This one here also comes neatly out of the unit circle. If I pull that triangle out here, of course, since it's the unit circle, my radius is 1. This is sine theta. This is cosine theta. This is a right angle triangle. And I can use Pythagoras. That's what this is. Sine square theta plus cos square theta is equal to the square of the hypotenuse. But the square of 1 is nothing else than 1. Hence, this identity here. Now, what we can do is we can also obtain these identities by simply working with the basic definitions of the sine ratio, the cosine ratio, and the tan ratio. I'd like you to do this as an exercise yourself. So what we'll do, or the way to start here, if you're interested in tan theta, you can start off like this. Tan theta net is equal to sine theta over cosine theta. Well, but sine theta is the adjacent over the hypotenuse. So the adjacent over hypotenuse. Big fraction bar, cosine theta. Well, cosine theta is the side B here. Oh, sorry, A is not the adjacent, it's the opposite. I got confused with letters. So it's the opposite over hypotenuse, and cosine is side B over the hypotenuse. And now rearrange this in order to show that eventually you get to this definition here, opposite of adjacent. And repeat the exercise here also. So you can stop the video now and do this, try to do that for yourselves. Now, there's a whole load of other trigonometric identities. In fact, pages and pages of them. But the most relevant to us will be these here. I want to say a little bit where they come from, and I want to focus on this one here for the moment. And I'll show you a few things about this on autograph. So, here I have the sine curve and the cosine curve drawn with dashed lines. Now, what would happen if we plotted a curve that actually goes like this? Y equals sine A times sine x times cos x. If I press enter, I'm getting, well, first of all, A takes automatically the value of 1, and we're getting this curve here in purple. That curve is pretty obvious. Well, I say it's sine x times cos x. Well, sine x was 0 here, and cos x is 1, so 0 times 1 is 0. That makes sense. 1 times 0 is also 0. That makes sense. And here, I'm about 0.7 something times 0.7, the same something. Okay, that should be about 0.5, so it's not surprising that I get this curve. Okay, and here also you can see a positive value multiplied by a negative value here will result in this value that looks around negative 0.5, etc. All these points make somehow sense. Now, if I